After introduction to refrigeration and air conditioning and refrigerants, we will be discussing vapor compression refrigeration system. In vapor compression refrigeration system, starting with simple vapor compression refrigeration cycle, then it's little bit extension of subcooling and superheating, and this vapor compression system with respect to its pressure and temperature diagrams, then actual vapor compression cycle along with different losses and actually what is happening, and in last the comparison of vapor compression cycle with air refrigeration cycle. So there are four major components in the refrigeration system. So first of all, if you start with the compressor, so in the diagram you need to identify the compressor, where it is located. If you look carefully, in the central part of this diagram the compressor is located. It is connected with condenser and evaporator. So on the left side of the diagram condenser is represented, while on the right side of the diagram evaporator is represented. So the condenser is connected with compressor, while condenser is again connected with the filter dryer, TX valve, and then evaporator, and then again back to the compressor. This TX valve is thermal expansion valve. So basically there are four major components of any refrigeration system, which is known as vapor compression refrigeration system. First is compressor, second is condenser, third is expansion valve, and fourth is evaporator. So compressor is a device which consumes maximum power, while condenser and evaporator are the heat exchangers. Expansion valve is the basically metering device which regulates with respect to flow movement. In this refrigeration cycle, two different pressure exist. One, the evaporator or low pressure side, while in the condenser is known as high pressure side. Low pressure evaporator, high pressure condenser. Evaporator is used or represented as green. It is used to circulate low temperature zone, while condenser is represented by the high pressure zone, is related with the high temperature zone. So on the one hand, these two components are divided into metering device which control the refrigerant, and other end it is the compressor. So two condenser evaporator, two heat exchanger, and compressor and expansion valve, or you can say metering device. In simple vapor compression refrigeration system, this is the pictorial representation of low pressure and high pressure side. So compressor, after compressing, then it is condenser on the right side of the diagram, the condenser to expansion valve. So this semicircle on the right side can be known as high pressure side, while the left side semicircle is known as the low pressure side. In condenser, heat is transferred from refrigerant to outside air, while the evaporator, heat is transferred from inside air to the refrigerant. In this basic representation of refrigeration cycle, the compressor is the starting point. On any PV and TS diagram, the starting point is compressor, which is known as starting point 1. So the compressor is represented in that diagram on the extreme right side. One motor type of device is shown. So when we start with the basic refrigeration cycle with compressor, starting at the compressor, right, then low pressure vapor refrigerant, which is compressed in the compressor. It is a hermetically sealed reciprocating type of compressor which is generally used in household refrigerator and air conditioners. So this low pressure vapor refrigerant is compressed and discharged out of the compressor. Okay, so you look carefully, it is already representing in this diagram that green color particles are moving from the compressor towards the blue side. So this low pressure vapor refrigerant is compressed and discharged out of the compressor. After discharging the compressor, the refrigerant at the point is a high temperature, high pressure, and sometimes or most of the times it is a superheated vapor. The high pressure refrigerant flows to the condenser by the way of discharge line. Okay. Then the condenser changes the high pressure refrigerant from a high temperature vapor to a low temperature high pressure liquid. So all vapors is converted into liquid and leaves to the liquid line. The high pressure refrigerant then flows through a filter dryer to the thermal expansion valve, which is previously known as TX valve. This TX valve meters the correct amount of liquid refrigerant into the evaporator. As the TX valve meters the refrigerant or measures the refrigerant amount of refrigerant, the high pressure liquid changes to a low pressure, low temperature saturated liquid. This saturated liquid enters the evaporator and changes to a low pressure dry vapor. The low pressure dry vapor is then returned to the compressor in the suction line, and the cycle then start over. So high pressure is vapor is converted into low pressure dry vapor into evaporator before supplying to the compressor. Then again the compressor, this is converted into low pressure vapor is converted into high pressure superheated vapor. This simple vapor compression cycle generally consists of two additional features. One is superheating, another one is subcooling. So what is superheating and what is subcooling? Superheating is the incident where the liquid is heated above its boiling point. So the critical line on the right hand side, if we enter towards the zone beyond this line, then it's superheating. So after the liquid is leaving the evaporator and heading towards the compressor, there should not be any hint of liquid present in the vapor. This tiny amount of liquid can damage the compressor as well, and it automatically surpasses the line, the saturated line, so it enters in the superheated zone. In subcooling, where the process is cooled down below its condensing temperature or condensation line on the left hand side, so the temperature will occur, this vapor turn into the liquid. So when suppose a refrigerant is cooled and turned into a liquid, but cooling will not stop at the saturation line, it will continue to cool. So therefore it will enter in the subcooling zone. So without subcooling, the refrigerant will not flow the next line and head towards the expansion valve. Therefore subcooling is the required procedure during the flow of expansion valve to the evaporator. The analysis of vapor compression cycle considering degree of subcooling and superheating is done into two different steps: measure subcooling of measure superheating. So where it is located and how do we measure? So first of all, the saturation pressure and temperature is required throughout the cycle, and one chart is drawn. So the pressure reading in the subcooling, the pressure reading of the liquid line leaving the condenser is required to be noted down, while for superheating the pressure reading leaving the evaporator is required to be noted down. So condenser and subcooling, evaporator and superheating, the reading is required to be the refrigerant saturation temperature and the pressure temperature when refrigerant turned into the high pressure vapor into the high pressure liquid, high pressure vapor to high pressure liquid, it gives up some heat. So when it gives up some heat, there is some variation in the temperature, should be noted down. Then convert this pressure temperature with respect to pressure temperature chart. Then take the temperature reading at the moving liquid at the line of the condenser. And then we need to compare both, that at the standard rate this should be the temperature and pressure, and if it is entered in the subcooling zone, that is the difference. We can say how much amount of subcooled liquid is obtained during that procedure. Similar reading can be done for the superheating case. So the difference between standard to the actual data can be calibrated and measured. So now in diagrammatically it is represented now. The left hand side picture represented the simple vapor compression cycle, or you can say ideal cycle also. So there are two possible ideal cycle, Carnot cycle or Rankine cycle. If we drawn in the diagram, actually these are the reverse cycle. So from 1, 2, 3, 4, if we draw two horizontal line from 1 and 3, so 1 to 2C and 3 to 4C. If we identify that diagram 1, 2C, 3, 4C, so this is nothing but the reverse Carnot cycle. And this zone from 1 to 2B, so beyond that zone is known as basically superheating, subcooling on the left hand side 3 to 4L, basically this side. If liquid enter to that side, that can be considered the subcooling liquid. So this reverse cycle, or you can say dark cycle 1, 2C, 3, 4C is reverse Carnot cycle. And if we entering in the 2R, 1, 2C, 2R, then it is the representation of Rankine cycle. While from next bottom side, if it is going to represent it, 4L is also the part of the Rankine cycle also. So ideally it's 1, 2C, 3, 4C. This is the representation of Carnot cycle. On the right hand side, the pH diagram for this vapor compression cycle with subcooling and superheating is drawn basically. So these two diagrams are entirely different. One diagram is representing the standard cycle, standard Carnot cycle, reverse Carnot cycle, and the right hand side diagram is representing the practical or actual vapor compression cycle with subcooling and superheating. So where is subcooling and where is superheating? It is very easy to find out. So this is the PV diagram, not TH diagram. So TH diagram is different, pH diagram is different. So because pressure is the most important part from compressor to condenser, as well as before compressor to evaporator. So superheating is represented during the compression process, and then during the expansion process subcooling is represented. So the cycle is represented 1 to 2. So if some amount of liquid is present in the compressor, one cycle starts. So during the continuous running of the compressor, the superheating start instead of 1, it start from 2, I mean the compression part. So 1 to 2, then 2 to 3 is the compression part, and again 3 to 4 desuperheating, because it is going to back to the saturation line. Then 4 to 5 is condensing, then 5 to 6 you can say it's a subcooling part, then 6 to 7 again expansion, and 7 to 1 again evaporation. So this is again representation. Earlier we have seen the representation of PV diagram. This is the representation of TS diagram with subcooling and superheating. So 7 to 1, this is the evaporation. 1 to 2 and 2 to 3 is the superheated working during the compression process. So there are two pressure zone, PL and PH. PL is P low pressure, PH is the high pressure zone. So 2 to 3 means PL2, or increasing the pressure from PL to PH. Similarly the temperature is also rises. Then from 3 to 4 the superheated vapor is cooled to the saturated vapor, or you can say it touches the saturation line. Similarly the isothermal condensation of the saturated vapor also gives you the value of T4 to T5, because temperature line is constant. So 4 to 5 and 1 to 7 or 7 to 1 is the constant temperature line. Okay. So liquid's refrigerant is subcooled in the temperature T6 to T5, or basically it is going to reduce its pressure from T5 to T7. Basically T high to T low is represented on the temperature diagram. The expansion of the refrigerant takes place at the constant enthalpy basically. So this is just a representation of compressor, how it looks like. Basically the compressor is the main part of vapor compression reference system, which consumes power and gives the better efficiency as well as the higher cost. So it is known as the heart of the system basically. So it compresses the low pressure refrigerant vapor from evaporator and compresses to the high pressure vapor. Generally the compressor inlet is known as suction line, and compressor outlet is known as the discharge line. It is a representation of condenser basically. So condenser is attached to the compressor on the top side, and the bottom side the evaporator attached to the compressor. So the discharge line of the compressor, outlet of the compressor, is connected to the condenser. So condenser is nothing but the heat exchanger. So cool air blown across the outside of the fin tube of the condenser. Similarly, since the air is cooler than the refrigerant, then heat jumps from the tubing to the cooler air. Basically energy goes from hot to cold, simple fundamental of latent heat. So as heat is removed from the refrigerant, it reaches the saturation temperature and state changes. The high pressure liquid leaves the condenser through the liquid line and travel to the metering device, or metering device is the expansion device. Sometimes this metering device which is connected to the condenser, in between that condenser and expansion valve, a filter dryer is connected, so that any dirt or any foreign particles shall be collected and removed from this line. This is the example of metering device, the basically expansion valve. So metering device is regulate how much liquid refrigerant enters the evaporator. Metering device is connected between condenser and evaporator. Therefore, it is going to regulate the how much liquid refrigerant enters the evaporator. So thermal expansion valve are generally the devices which is used and having single opening, which is known as orifices. So the superheat as well as subcool also the part of metering device. As the metering device regulates the amount of refrigerant going to the evaporator, the device let a small amount of refrigerant out into the line and loses the high pressure it has behind it. Therefore, low pressure cooler liquid refrigerant entering the evaporator coil. Some pressure went down, so temperature goes also down. This is example of thermal expansion valve, continuation the previous slide. So thermostatic expansion valve, it is the capability of controlling the refrigerant flow according to the fluctuation of load. So it responds with the change and increase of the load to the flow. It has a sensing valve attached to the outlet of the evaporator. This valve senses the suction line temperature and sends the signal to that thermal expansion valve, allowing it to adjust the flow rate. Sometimes it is also better to use this valve, so that some mechanical damage to the components, it is automatically regulate the flow and stop the further accumulation of refrigerant into the discharge and suction line. This thermal expansion valve are set to maintain 10 degree of superheat, basically difference of standard to the superheated part. So it regulates between these amount. If we go beyond that, it automatically ceases the flow. The evaporator is the main device where the heat is removed from the designated space. So low pressure liquid leaves the expansion valve and enters the evaporator. Generally, a fan is used to move warm air from the conditioned space across the evaporator fin coil. The cooler refrigerant in the evaporator tubes absorb the warm room air and changes the temperature from low pressure liquid to low pressure cold vapor. The low pressure vapor is pulled into the compressor and cycle starts. The amount of heat added to the liquid and makes saturated, and therefore the state is called superheated state. It is the representation of actual vapor compression cycle, where process 1 to 2 is represented by a irreversible and non-adiabatic compression of a refrigerant, where heat is transferred from the surrounding to the refrigerant and entropy increases. From 1 to 2 prime, heat transfer from the refrigerant to the surrounding, so entropy is basically decreased, and therefore higher amount of entropy is the starting point, while the lower amount of entropy at the end point 2 prime. 2 to 3, from the top side, temperature and pressure drop due to the fluid friction and heat transfer. Then 3 to 4, pressure drops in the condenser due to fluid friction. 4 to 5, temperature pressure drop. Then 5 to 6, throttling process. 6 to 7, again throttling process, and 7 to 1 is the expansion. So this is the actual cycle. So the compression part is mostly on the above the saturation line, therefore the superheated liquid is generally used during the inlet and outlet of the compressor. Similarly, on the subcooled zone is very much little bit is between 4 to 5, therefore less subcooling is the part of standard actual vapor cycle. And we have seen that this isothermal process, isothermal condensation and evaporation, actually there is a slight temperature variation when pressure falls and temperature increases. So what is the difference between actual and theoretical cycle, vapor compression cycle? This is mainly due to losses and friction. The vapor refrigerant leaves the evaporator is in superheated state, that is another cause. Apart from that, the refrigerant, the compression of the refrigeration is neither isentropic nor polytropic, because due to the presence of some superheated condition vapor. The liquid refrigerant before entering the expansion valve is subcooled. This is also the cause of deviation from standard cycle. Also the pressure drop, which is occurred in the evaporator as well as in the condenser. Now there are two cycles, vapor compression cycle and unused cycle, which is known as gas compression. So air is the gas, therefore it is known as air refrigeration cycle. So vapor compression and air refrigeration cycle, it is a starting point of the air refrigeration as well. So we need to understand what is the difference. First is the type of refrigerant. In vapor compression cycle, different refrigerants or fluid, liquid like freon, ammonia, CFCS, CFC, like we have discussed, the refrigerant part is used as a refrigerant, and in gas cycle air is used as a refrigerant. Second difference is that with the heat exchanger. In vapor compression refrigeration cycle, condenser and evaporator are the two heat exchangers which absorb and gives up the heat, and the refrigerant undergoes the change in phase, while in the gas cycle, air refrigeration cycle, the exchanges heat in the heat exchanger, but there is no phase change of the gas. So the difference is phase changes in the vapor compression, while no phase change in the air refrigeration. The efficiency of vapor compression cycle is more than the gas cycle, because for the same amount of refrigerant effect, because in that particular part large volume of gas is required. So for the same efficiency system, the air refrigeration cycle becomes bulky and expensive, which is also not advisable for domestic application. Third difference is with respect to cycle use. The vapor compression works on the reverse Brayton cycle, while the gas compression works on the reverse Rankine cycle. Now the application is the fourth major part. In vapor compression cycle is the cycle which is mostly used for the refrigeration purpose, for household refrigerator, air conditioner, water cooler, ice and ice cream makers, cold storage, as well as deep freezers, large industrial refrigeration, air conditioning systems, central air conditioning as well. While the size of gas compression system is very large, they are used for the domestic industrial purpose, like for big factory. Also they are widely used in the aircraft air conditioning. So for aeronautical engineering students, it is important to understand that they are going to understand the gas refrigeration or air refrigeration cycle, in order to understand the aircraft air conditioning system. Why? Because the aircraft air is very high pressure is available at higher side, I mean when aircraft is in running condition, so we don't need any air compressors for compressing the air is available at very high pressure. So this makes the air conditioning system in the aircraft lightweight and less power consuming. So the use of air as the refrigerant in the aircraft prevents the danger of fire also from the flammable refrigerant, because few refrigerants are flammable. This is the advantage of air refrigeration cycle. So with that, the standard vapor compression refrigeration system is over. Next we will understand the different type of aircraft refrigeration systems.